I would like to introduce you to Freddy the Frog. Freddy the Frog is right here, and we're going to be talking about him throughout the unit. And we're going to use Freddy the Frog to introduce you to the graph of the sine function. In this application, Freddy the Frog is riding on the circumference of a windmill on a mini-putt course as it rotates counterclockwise. So here's the water, here is the mill wheel. Here is Freddy the Frog. You have to know that the radius of the mill wheel is 1 meter. So from the center to the edge is 1 meter. And Freddy is going to be riding around the outside, the circumference of the mill wheel. And what we're going to be looking at is the graph made by Freddy the Frog while traveling on the mill wheel. And we're going to be comparing his height above or below the water as a function of the angle that he has rotated. So on the x-axis will be the degree or the angle that he's rotated. So if he rotates 30 degrees and he's up here, what's his height? If he rotates 45, he's up here, what's his height? If he rotates 60, what's his height? If he rotates 90, etc., 135, 180, etc. What is his height is on the y-axis, and the amount of rotation is on the x-axis. So think about what that will look like. So we're now going to look at this interactive application here. So here's Freddy the Frog right here, this green dot, and here he is. There's been no rotation. He's sitting on the right side at the water level. So his height is currently 0, and we can put that into a table here. So after no rotation, his height is 0. Now if we were to rotate him 15 degrees and measured his height, then we would find out that his height is approximately 0.26. So in our table, we can say that after 15 degrees of rotation, his height is 0.26 meters. Now, if we rotated him 30 degrees, his height here would actually be exactly 0.5 meters. So we could put that into our table and rotate him 45 degrees, and his height would be approximately 0.71. And we could keep doing this over and over again. Measure his height at 60 degrees, measure his height at 75 degrees, all the way up to when he gets to 90 degrees. Because the radius of the wheel is 1 meter, he's up at 1 meter tall. So we can do that. Then, if you look at the symmetry of the wheel, once he rotates to 105 degrees, it's actually going to be the same height as when he was at 75 degrees. And run 120 degrees, the height after that rotation is going to be the same as the height at 60 degrees, etc. So all the way down until we get to 180 degrees of rotation and get back down to the water level, which gives him a height of 0. All of those numbers are going to be the same as these numbers, just backwards. So we've gone from 0, we've gone up to a height of 1, that's the maximum height, because that's the radius of the wheel. And then as we approach 180 degrees of rotation, we've gone back down to 0. Now, as he goes below the water, his height is going to be negative. So when he rotates to 195 degrees, it's going to be the same height as it was at 15 and as it was at 165. It's just now going to be negative. His height at 210 is now going to be the same as his height at 30 degrees, and his height at 150 is just going to be negative. So his height is at negative 50. So as he progresses this way, his height is going to go to a minimum of negative 1. Again, that's the radius of the wheel. So his minimum height would be -1, so that's 1 meters below the surface level of the water. And that takes us down to 270 degrees. All the same numbers again, but now they're negative, and now they're going to -1. Lastly, in the last part, once again, because of symmetry, the numbers are all going to be the same, but now the numbers are going to approach back to 0. And that would complete one full rotation of Freddy's ride around the wheel. If we were to graph that data, this is what his graph would look like, comparing the amount of rotation in degrees to his height above the water. And then I just changed the scale a bit so it matches up our graph. So every 15 degrees of rotation, you can see his height. And this should remind you of the sinusoidal applications that we did, because it's a wave. And remember, sinusoidal applications sometimes start at the maximum, sometimes start at the minimum, sometimes start on the axis and go up, sometimes start on the axis and go down. But an actual, if it's a sine function, not a sinusoidal, a sine function, and a sine function is a type of sinusoidal, but a sine function starts on the axis and heads up. So at 0 degrees of rotation, the height of Freddy is at 0. The next key point would be at 90 degrees. At 90 degrees, Freddy is at his maximum, which is 1 meter. The next key point would be at 180 degrees. So at 180 degrees, his height would be 0, and he would be on the axis. And at 270 degrees, the next key point here, his height would be at -1, and the last key point at 360 degrees, his height would be at 0. So the same key points exist. So from the start, your key points happen 4 times in a cycle. So an entire cycle takes 360 degrees. So if you divide that by 4, you get 90. So every 90 degrees, your key point changes. So 90 degrees, you're at the maximum. 180 degrees, you're at the axis. 270 degrees, you're at the minimum. And 360 degrees, you're at the axis. This is a sine curve. Sine as in S-I-N-E, and sine referring to sine, cosine, and tangent. This is the graph of y equals sine x. So Freddy's ride along the mill wheel is an example of the sine function. And if you were to continue to go around, it's all just going to repeat. So after 360, if he goes another 15 degrees, that is at 375, and the numbers would just keep repeating over and over again. So you can see here that the numbers here are all the same again as the numbers are here. So here's another example that you can see the connection and see it happen at the same time. As the point Freddy is P, as it goes around, you can see how the graph will make its curve, and as it continues past one cycle and goes into another cycle, how it's going to continue. So you can see it is a sine curve starting on the axis. As Freddy starts here, it goes up to a maximum of 1, back to the axis, down to a minimum of -1, back to the axis. These key points change every 90 degrees because one full cycle is 360 degrees. And 360 degrees divided by 4 is 90, so that's the key points are changing every 90 degrees. And because this is periodic, the graph will repeat and it will repeat, and if we continued, it would keep on repeating over and over again. Now, if we remove the fact that this was an application of Freddy going around the wheel, around and around and around, we could also consider negative exponents. Negative exponents could also kind of mean Freddy going in the opposite direction. So instead of going this way, positive, he would go this way, and then he would be going into negative degrees of rotation. So that means the graph could also continue to the left and just repeats itself over and over and over again. So anything to the left of the x-axis could be considered Freddy the Frog just either going back in time or just rotating in the opposite direction. So rotating this way instead. So this is the graph of Freddy the Frog, and Freddy the Frog represents the sine curve, which is y equals sine x. And anytime you need to graph y equals sine x, I want you to think about Freddy, or in this case sine theta, because theta can be used as the variable for the degree of rotation. Anytime we graph y equals sine x or sine theta, I want you to think of Freddy's ride along the mill wheel. And the last thing I want to talk about is, why is this the graph of y equals sine x? And the reason why is, if you take a look at this, the circle being the wheel and this point being where Freddy is, the radius of the wheel is 1 meter, and we're measuring the height of Freddy's the height of Freddy above the water. If, for example, after 30 degrees, to find the height, the h is the opposite side, and the radius of the wheel, 1 meter, is the hypotenuse. So the ratio that compares the opposite to the hypotenuse is the sine ratio. So because we're solving for the height, which is the opposite side, and we know the hypotenuse, which is 1, that is why it is the sine. If we were looking for this distance, then it would be cosine, but we're not. We're looking for this distance here, the height. So that is the opposite, and we know the hypotenuse, so that is using the sine function, and that is why this is the graph of y equals sine x.